which is on derivatives of exponential and log functions. The intent is to try to do this video in two parts, where the first part will be on pages 1 and 2 of the section 3.9 notes, and part 2 will be on pages 3 and 4 of the section 3.9 notes. So here we're starting with a calculator exploration, and you can see here that we want to plot e to the x and then the derivative of e to the x. And the hope is that we can discover what the derivative is graphically without me just telling you what the derivative is, and then try to get a good understanding of it. So what I'm going to do is I'm going to pull up this calculator app called the Wabbit, and you can definitely have your calculator out when you're doing this. So let me go ahead and clear these equations here, and I'm going to graph e to the x. Remember, e is right there, it's second ln. And then alpha window is where I can find the shortcut for derivative, or nderiv. Takes respect to x of e to the x. And because your graphing is for all x values, you need to say x equals x. And also, just so I can distinguish my second curve from my first curve, if I go to the left of y2, I can make that darker. Another thing that will be helpful is if I go to mode, make sure sequential is selected. That way it won't do both graphs at the same time. We'll do one graph and the second graph. And also we're going to go zoom 4. That way the window will make it a little easier to see what's happening. It kind of reduces the number of tick marks for x and y if you choose option 4 to see the decimal. So we see e to the x is right there, crosses y-axis at 1. And then the derivative of e to the x is coming. It's a thicker line. And we see how it's basically going to be the same graph. And that kind of makes sense, because if we look at e to the x, all the tangent lines will be positive, and the derivative kind of follows the same thing. So we notice that e to the x derivative is probably just going to be the same thing. So we're going to say the derivative of e to the x is e to the x. So we notice they're the same graph. Now, if your exponent's not plain old x, if it's something else, like say for example, in this case here of e to the 5x or e to the x squared plus 3x, we're still going to say it's e to the u, but then we're going to have to do the chain rule. So derivative e to the u is e to the u times du dx, just using the chain rule. So in this case here, if I want to find the derivative of e to the 5x, it will be e to the 5x, but then times the derivative of 5x, which will just be 5. So e to the 5x times 5, or you can write it like that. Likewise with example 2. You have e to the x squared plus 3x times derivative with respect to x of x squared plus 3x, which will just be 2x plus 3. Or you can actually write it, hold on, e to the x squared plus 3x times 2x plus 3. So that works for us too. So pretty simple. The derivative e to the x is e to the x, but of course you don't have plain old x. Still have it e to that power, but then times the derivative of the exponent, because that's chain rule. Now let's look at 2 to the x power. So I'm going to come back to my calculator and replace that with a 2. Replace that with a 2. And we're going to, gotta be careful, gotta raise it to the x power. Good thing I noticed that. Okay, now let's go and graph it. So there's 2 to the x. And then the derivative is coming. Looks like it's going to be about the same curve. Oh, but not quite. Looks like it's slightly below 2 to the x. So 2 to the x look like this. Okay, let me erase that. Sometimes there's a bit of a lag with my laptop. And then the blue curve will look like this, where I'm making this blue and I'm making the first one red. If I go back to y equals, and under y3, if I do y2 divided by y1, so y2 divided by alpha trace. Alpha trace is how you can call up any equation you stored under y1, y2, or anything under y equals. And let me turn off the first two graphs, just so we don't see them. And we're going to notice something interesting with y2 divided by y1. It's going to be a constant. And it's taking a sweet little time because it's trying to graph each of them, trying to figure out what they are, and also calculate the derivative for y1, because y2 is the derivative of y1. And we see how it looks like it's slightly less than 1. In fact, if I trace, we see that we get 0.693. So that's a bit interesting. It seems as though y2 divided by y1 is going to be 0.693. So it's just a horizontal line. Or it seems that my derivative of 2 to the x is going to be 2 to the x times 0.693. So that's something that we're noticing with the derivative. It seems like that we're when you take the derivative, it looks like it's the same as 2 to the x, but times the constant, that being 0.693. Let's look again. And if you're kind of unsure why we get 0.693 for this portion over here, remember what y2 y1 represents. d over dx, 2 to the x, or 2 to the x, right? So d over dx of 2 to the x over 2 to the x equals 0.693, which is what we got when we did y2 over y1. And so, of course, the derivative of respect to x of 2 to the x will be 2 to the x times 0.693. So hopefully you're able to see the algebra behind that. And I didn't quite explain that just a minute ago. All right, so now let's look at another one. Let's say if I did 10 to the x. We probably should see the same phenomenon here. And let me turn off y3 for now. Okay. So there we get 10 to the x power, and then that's going to be the derivative of 10 to the x. So it looks like now it's a little bit above 10 to the x. So if that's red and that's blue, the red curve look like this. The blue curve will look like that, roughly. If I go back to my calculator, and graph y2 over y1, we see it's going to be slightly higher than 2, about 2 point something. So in this case, I'm going to graph that. And if I hit the trace button, we get 2.303. So y2 over y1 is 2.303, or it seems that the derivative of 10 to the x is 10 to the x times 2.303. So let's actually think about what's happening to the derivative of a to the x analytically. Now, we can think of a to the x as e to the p power, just doing a straight substitution, letting a to the x equals e to the p. If I take the natural log of both sides, And remember your log properties. If you have log of something raised to an exponent, it's n times log x, right? So in this case, x times natural log of a will equal p times natural log of e. Remember, natural log of e is just 1, so p equals x times the natural log of a. Or we could say that a to the x, which equals e to the p, will be e to the x times ln a. So that's what we have here. Y equals e to x times ln a. So y prime, if I do what I did earlier, is just e to the x times ln a, but then times the derivative of our exponent, will just be ln a. Remember, ln a is just going to be a constant. So again, this right here is just using the chain rule, which will be the derivative. Okay, there we go. Derivative of x times natural log of a. So I have natural log of a times e. Now, because p equals x ln a, I could substitute for x ln a and put p in its place. And because e to the p equals a to the x, our derivative a to the x is just natural log of a times a to the x. So natural log of a, but then parentheses if you like, times a to the x. That'll be the derivative of any base raised to the x power. And of course, you could do the same thing. If you did d over dx of e to the x power, where now your a is e. Same thing, Natural log of e times e to the x. Of course, natural log of e is 1. So we get back to e to the x, which we had on the first page. So here we have, if we have an exponent that's not plain old x, like we'll call it u, it'd be kind of the same thing, a to the u times ln a, or if you just want to go in the same order, doesn't really matter because multiplication is commutative. Come on. ln a times a to the x times du over dx. So if you look at some of these examples, like y equals 10 to the x, y prime will be 10 to the x times the natural log of 10. Natural log of 10, by the way, was 2.303, which is what we saw when we did this graphically, right? And by the way, natural log of 2 is 0.693, which we saw on the first page. So for this one, y prime will be 5 secant x times natural log of 5. But then we got to do the chain rule as well. And derivative of secant x is secant x times tan x. So that takes care of derivative of exponential functions. In part 2 of the video, of this video lesson, I will now talk about derivative of logarithms.